All right, hello everyone. Welcome to week 6 for Maps, Mapping, and Geospatial Technologies. Today we're going to be talking about geoprocessing and spatial analysis. So I'm just going to jump right in. So spatial analysis is the examination of the characteristics or features of spatial data and how features spatially relate to one another. Anytime you are examining the spatial characteristics of data or how objects relate to another across distances, you are performing a spatial analysis. Spatial analysis, the analysis functions of a GIS are use both spatial and non-spatial data. Sorry, I have Cora, who is being a little bit of a butt right now. She's a little needy and wants some attention, but spatial analysis helps us answer questions like how many objects of a particular type are within a certain distance of a particular location. How do you choose the most suitable locations based on a set of criteria? So the most distinguishing purpose of a GIS, the operations that use spatial data to derive new spatial information. Spatial location distinguishes GIS from non-spatial analysis. Think about something like how many rental properties are within 2 blocks of this specific elementary school, or how many acres of wetland will be threatened by this proposed new development. Data attributes distinguishes GIS from non-GIS mapping software. I think about how many houses are for sale in my price range, or how many acres of wetland have black spruce trees on it. Comparative spatial analysis provides the correlation of variables across space, wetlands clusters at local scale versus uniform at regional scale, and statistical spatial data analysis. So think back to a couple weeks ago where we took a look at John Snow investigation of the chloria outbreak in Soho, central London in 1854. His analysis of a poor, overcrowded square mile of narrow streets and alleyways was able to identify the infected water from one pump as the source of the outbreak. Snow mapped the locations of the chloria deaths in relation to the water pumps. 11 locations showing water pumps are marked across the map. 2 water pumps are marked to the northeast of Oxford Street. 1 pump is marked to the southeast of Oxford Street. 1 more pump is marked to the northeast of Regent Street, and another is marked to the southeast of Regent Street, close to Golden Square. 1 pump is marked to the south of Savile Row, and 1 pump is marked to the northeast of Piccadilly. 1 pump is marked to the north of Brewer Street, and 1 more at southeast of Brewer Street. 1 is marked at the middle of Broad Street, and the last pump is marked at the southern end of Dean Street. Deaths from chloria are most frequent surrounding Broad Street and the region adjacent to Wardle Street and Dean Street. The region north of Brewer Street also shows many deaths related to chloria. The relation south of Brewer Street has points representing chloria deaths scattered around. The region west of King Street also has numerous chloria-related deaths. The region to the east of Scaville Row has a few chloria deaths marked. This type of spatial analysis was innovative for his time, but is now a routine problem that can be solved with modern-day GIS. So retrieving data for analysis, a query sets the conditions used to retrieve data from a database. You can select all districts that have a Democratic representative, select all houses that have been sold in the past month. Queries can also create subsets of data, select all districts in New York that have a Democratic representative, select all houses in Rochester that have been sold in the past month for less than $400,000. One type of GIS-related analysis involves finding which areas or locations meet particular criteria. For instance, using a map of U.S. congressional districts, you might want to identify which districts have Democratic representatives and which have Republican representatives. Alternatively, you might have a map of all residential parcels and want to identify which houses have been sold in the past month. Both of these examples, you would perform a database query to select from the attribute table only those records that reflect the qualities of the objects with which you want to work. In other cases, before beginning the analysis, you might only want to utilize a subset of your GIS data. For instance, rather than deal with all congressional districts in the entire United States, you might want to examine only those in Ohio. Or if you have a data set of all residential parcels in a country, you might only want to do analysis related to one or a handful of the parcels rather than examine them all. You'd want to go into the data set and select only the parcels required for your study. Again, in these cases, the query would select only the records you want to deal with. In GIS, queries are composed using structured query language, or SQL, whose format is much like that of a mathematical function. SQL has a specific format that is used for querying a layer or database to find the attributes that meet certain conditions. For instance, a layer made up of points representing cities in Ohio also has a number of fields representing its attributes, such as city name, population, and average income. If you wanted to do analysis with one of these records, then the query city name might equal Boardman could be built into to find all records where the field called city name contains the characters Boardman. This query should return one record for you to use in your analysis. Another example would be to select all cities in Ohio with population greater than or equal to 50,000 persons. The attribute table has a field called POP 2010 that contains this information. Thus, the query POP 2010 less than or equal to 50,000 could be built in all records with population fields containing a value greater than or equal to the number 50,000 would be selected for your query. This is an example of a compound query that contains more than one operator as a way of linking multiple criteria together. For relational operators, we have four different kinds of them. We have equal to. You use this when you want to find all values that match the query. For instance, city name being equal to Poland locates all records that exactly match the characters in the string that comprise the word Poland. If the record were called Poland Township, the query would not locate just Poland because it looks for an exact match to the character string. Not equal, use this when you want to find all the records that do not match a particular value. For instance, the query city name does not equal Poland returns all the records that do not have the character string Poland. Greater than or equal to, use these operators for selecting values that are more than or equal to a particular value, and then similarly for less than or equal to, use these operators for selecting values that are less than or equal to a particular value. Boolean operators, again, we have four. So we have and. Suppose you want to select cities in Ohio that have a population of over 50,000 and an average household income of more than 30,000. A compound query can combine these two requests as follows. So you would use POP 2010 greater than or equal to 50,000 and average household income is greater than 30,000. Because and is being used as the operator, the query returns only records that match both of these criteria. An AND query is referred to as an intersection because it returns what the two items have in common. OR query, say that you use the same query that I described for AND, population 2010 greater than 50,000, or sorry, greater than or equal to 50,000, or average household income is greater than 30,000. This would return records of cities with a population of greater than or equal to 50,000, or cities with an average household income of greater than 30,000, or cities that meet both criteria. An OR query is referred to as a union because it returns all the elements of both operations. NOT query, a query can be built around the concept that you want all of the data related to one criterion, but you want to exclude what relates to a second criterion. For instance, if you want to select cities with a high population, but not those with an average household income over 30,000, you could build a query like population 2010 greater than or equal to 50,000, not average household income greater than 30,000 to find those particular records. A NOT query is referred to as a negation because it returns all the elements of one data set, but not what they have in common with the other. And last but not least, we have NOT OR. A final type of query can be built using the idea that you want all the data from each layer except for what the layers have in common. For instance, if you wanted to find cities with a high population or those with high incomes but not both types of cities, your query would be population 2010 greater than or equal to 50,000, NOT OR average household income greater than 30,000. NOT OR works as the opposite of AND because it returns all data except for the intersection of the data set. A NOT OR query is referred to as an exclusive OR because it acts like a union but leaves out the intersection data. Analysis functions for non-topological functions. So evaluates the attribute values of spatial data, and it uses SQL, select, join, etc. So you'll have your Boolean operators, your relational operators, and then your arithmetic operators, which we did not cover, but arithmetic operators are addition, subtraction, multiply, and division. And then we have a couple different examples, and this image is a pretty good representation of what each one does. So for non-topological functions, well, let me back up. So topology, hopefully you guys remember when we covered it a couple weeks ago. Topology is how vector objects relate to each other in terms of their adjacency, connectivity, and containment independently of the object's coordinates. Spatial analysis can have topological functions and non-topological functions. Non-topological is an intermediate step to obtain new attribute data to support specific spatial analyses. For non-topological functions, statistical computation of non-spatial statistics. This would be the mean, maximum, minimum, range, standard deviation, and frequency, and so on. You also have the spatial calculation of spatial statistics, which would be area, perimeter, distance, proximity. Spatial matters, projections, and coordinate systems. Just keep that in mind when you are doing your calculations. And for topological functions, we evaluate individual data objects, feature-based or layer-based. Feature-based analysis find relationships between features and layers. This would be overlay, buffer, union, point in polygon, line in polygon, etc. How many residential homes are in this voting block, and how many farms by field are in this county. So what is spatial analysis? It is how many X are within D of Y. So GIS gives us the ability not only to perform a regular SQL style query, but also to perform a spatial query. To select records or objects from one layer based on their spatial relationships with other layers rather than use attributes. With GIS queries can be based on spatial concepts to determine things like how many registered sex offenders reside within a certain distance of a school, or which hospitals are within a particular distance of your home. The same kind of query could help a researcher determine which chloria deaths are within a buffer zone around a well. In these cases, the spatial dimensions of the buffer are being used as the selection criteria. All objects within the buffer will be selected. Geoprocessing is to do spatial analysis along the lines of John Snow's hunt for a chloria source. You have to be able to do more than just select a subset of the population who died, or just select the locations of wells within the area affected by the disease. You have to know something about how these two things interacted with each other over the distance. For instance, you need to know something about how many chloria deaths were found within a certain distance of each well. Thus, you don't just want to create a buffer around one layer. Rather, you need to know something about how many features from a different layer are in that buffer. Many types of GIS analysis involve combining the features from multiple layers to allow examination of several characteristics at once. In GIS, when one layer has some sort of action performed to it, and the results is a new layer, this process is referred to as geoprocessing. There are numerous types of geoprocessing methods, and they are frequently performed in a series to solve spatial analysis questions. Analysis functions buffer. A simple type of analysis involves constructing a buffer around the elements of a data layer. A buffer is an area of proximity set up around one or more objects. For instance, if you want to know how many rental properties are within a half-mile of a selected house, you can create a half-mile buffer around the object representing the house and then determine how many rental properties are within the buffer. Buffers can be created from multiple points, lines, or polygons. Buffers are simple tools to utilize, and they can provide useful information when you're creating areas of analysis for various purposes. GIS can also perform a dissolve operation in which boundaries between adjacent polygons that have the same properties are removed and the polygons are merged into a single larger shape. Dissolve operations are useful when you don't need to examine each polygon, but only regions with similar properties. For example, suppose you have a land use map of a county consisting of polygons representing each individual parcel and how it's being used, commercial, residential, or agriculture. Rather than having to examine each individual parcel, you could use a dissolve on the boundaries between parcels and create regions of residential land use or commercial land use for ease of analysis. Similarly, if you have overlapping buffers generated from features, a dissolve can be used to combine buffer zones. So this is an example of a buffer. The demo shows a simple point buffer of 100 feet within a dissolve, and this gives a visual representation of buffer and can be used for further analysis. Topological overlay operators. Other analyses can be done beyond selecting with a buffer or selecting by location. When two or more layers share some of the same spatial boundaries but have different properties and are combined together, this is referred to as an overlay operation in the GIS. For instance, if one layer contains information about the locations of property boundaries and a second layer contains information about water resources, combining these two layers into an overlay can help determine which resources are located on whose property. Overlays are frequently used with GIS for combining multiple layers to perform spatial analysis. There is an intersect, which is a type of GIS overlay that retains the features that are common to two layers. Identity, which is a type of GIS overlay that retains all features from the first layer along with the features it has in common with the second layer. A symmetrical difference, which is a type of GIS overlay that retains all features from both layers except for the features they have in common. And a union overlay, which is a type of GIS overlay that combines all features from the two layers. There's also a clip, which a clip extracts only a part of a data set against a clip feature. Think of a cookie cutter. The output is whatever falls inside of the area. This example uses road centerline data against a subset of New York State Census tracts. Intersect and union. Intersect and union take two similar features and combine them together. Intersect only keeps the like parts, and union keeps all the parts but cuts where they are different. Oh, sorry. Cora decided she was going to switch sides. Okay. A merge takes two or more layers and combines them. Different than a union and intersect since it combines without analyzing geometry for likes. But what about raster data? That's where we have map algebra. Another way of performing a spatial overlay is by using raster data. With raster cells, each cell has a single value, and two grid layers can be overlaid in a variety of ways. The first of these is by using a simple mathematical operation, something such as math algebra, or is often referred to as math algebra, such as addition or multiplication. To simplify things, you can assign your grids only values of 0 or 1, where a value of 1 means that the desired criteria are met, and the value of 0 is used when the desired criteria are not met. Thus, grids can be designed using this system with values of 0 or 1 to reflect whether a grid cell meets or does not meet particular criteria. This type of overlay analysis is referred to as a site suitability because it seeks to determine which locations are the best for meeting certain criteria. Site suitability analysis can be used for a variety of topics, including identifying ideal animal habitats, prime locations when urban developments, or prime crop locations. When using the multiplication operation, you are left with sites classified as suitable, values of 1, or non-suitable, values of 0. Let's look at a simplified example. Say you want to find a plot of land on which to build a vacation home, and your two key criteria are that it can be close to forested terrain for hiking, and that it can be close to a river or lake for water recreation. What you could do is get a grid of the local land cover and assign all grid cells that have forests on the landscape a value of 1 and all non-forested areas a value of 0. You could do the same sort of thing for a grid of water resources. Any cells near a body of water get a value of 1 and all other cells get a 0. Therefore, the forest grid has values of 1 where there are forests and values of 0 for non-forest, while the water grids has values of 1 where a body of water is present, values of 0 for areas without bodies of water. Now you want to overlay your two grids and find what areas meet the two criteria for your vacation home, but there are two ways of combining these grids. In the image on the screen, this shows how the grids can be added and multiplied together with varying results when you multiply together grids containing values of 0 and 1. Only values of 0 or 1 can be generated in... Cora, hey, come on. You don't need to slap the monitor. When you multiply together grids containing values of 0 and 1, only values of 0 or 1 can be generated in the resulting overlay grid. In this output, values of 1 indicate where spatially both criteria, forests and rivers, can be found, while values of 0 indicate where both cannot be found. In the multiplication example, a value of 0 could have one of the criteria or none, but you're only concerned with areas that meet both criteria, otherwise you're not interested. Thus, the results either match what you're looking for or they don't. In the addition examples, values of 0, 1, or 2 are generated from the overlay. In this case, values of 0 contain no forests or rivers, values of 1 contain one or the other, and values of 2 contain both. When you use addition to overlay the grids, a gradient of choices is presented. The ideal location would have a value of 2. A value of 2, but values of 1 represent possible second choice alternatives. Value of 0 represent unacceptable locations. Using multiple data layers, GIS can process numerous large spatial data layers together at once. Thinking about the vacation home example, there are many additional factors that play into choosing the site of a second home, such as access to recreational amenities, the price of the land, the availability of transportation networks, and how far the site is from large urban areas. All these factors and more come into play when you're trying to find the optimal location for a vacation home. Similarly, if you work in the retail industry and are assessing which place is the best location for a new store, a lot of criteria will influence your decision, including how close the potential sites are to your existing store, how close that area is to similar stores, the population of the area, the average household income for each neighborhood, and the rental price of the property. GIS can handle all these spatial factors by combining them. A GIS model is a representation that combines these spatial dimensions or characteristics together in an attempt to describe or explain a process or to predict results. For instance, trying to predict where future urban developments will occur based on variables such as a location's proximity to existing urban areas, the price of the land parcels, or the availability of transportation corridors could be performed using GIS modeling, with the end result being a map of the places most likely to convert to urban land use. There are many different types of GIS models with different features and complexities, and it's far beyond the scope of this book to catalog and examine all of them. So this is an example of a model builder. So you have educational schools, which go into a buffer and output more educational schools based on the buffer. Same thing with daycare centers into a buffer and then output daycare centers. And then we grab the intersect, and this is where we get our feature class of the schools and daycare centers that overlap based on the buffers. So this is a video that I'm going to go ahead and play, outlining the image we just took a look at on the previous slide. Okay. So Python is an open source programming language. It was named after Monty Python. You can use it to automate and extend geoprocessing using a Python script. Access to all geoprocessing tool and a wide variety of other functionality in ArcPy. And you can extend other Python libraries. This is how we would declare Python variables. This is an example specifically using some ArcGIS. Python's a pretty standard scripting language that can be used for a multitude of different things, but in this instance, we're talking about it in a sense of using it for GIS and geospatial technologies. Same thing for Python statements, so we can import ArcPy and ArcPy.mapping, and then we can use just the standard Python statements in order to actually do stuff using ArcPy. ArcPy is a simple method to get to Python from ArcGIS. You can start your command with ArcPy. As you then work with a tool, it will help you fill out the other parts of the tool. And once you finish it, you can hit enter and it will run. So this is essentially a little command line built into ArcGIS Pro that you guys can use for a whole multitude of things. We're not going to cover it too much in depth in class, but we are going to kind of go through it and talk about it so you guys at least know what it is and how to use it. So to wrap up this lecture, we talked about spatial analysis and retrieving data using SQL. We talked about geoprocessing, all of the different operators for geoprocessing and map algebra. We talked about model building, and then lastly, we briefly touched on Python. So that is going to wrap up week number 6 for maps mapping and geospatial technology. You guys do have an assignment due this coming Sunday, the 23rd. I believe it's assignment number 4. Sometime this week, I'm also going to put out a quiz to cover chapters 4, 5, and 6. That is the end of the unit. So definitely keep an eye on that. You'll have a week to complete it, so don't worry. It's not gonna give it to you on Friday and then it's due Saturday. Just keep an eye out for it. I'll make an announcement once it is done and posted, and that is going to be it. If you have any questions about the midterm paper, feel free to reach out to me. I'm happy to answer them. Enjoy your week, everyone, and I look forward to talking to you.